Hi there, Ms. Barber here. This lesson is titled Optimization. We are now ready to explore some important applications of derivatives, namely optimization. The learning objectives for this lesson are: solve volume, area, and perimeter optimization problems. Solve maximizing revenue and profit and minimizing cost problems. And solve inventory control problems. A strategy for solving max-min problems are as follows. 1. Read the problem carefully. Make a drawing if possible and label any dimensions. 2. Make a list of relevant variables and constraints, noting what varies, what stays constant, and what units are used. Label the measurements on your drawing if you have one. 3. Translate the problem to an objective function f that expresses the quantity to be maximized or minimized. Represent f in terms of the variables of the previous step. 4. Use algebra and substitution as needed to express f as a function of only one of the variables. And 5. Use the derivative test, the second derivative test, and/or the extreme value theorem to determine the maximum or minimum values and the points at which they occur. Example 1. A store has 50 feet of fencing to fence off a rectangular area for a train set against the side wall of the store. The side against the wall requires no fence. A. What dimensions of the rectangle will maximize the area? Let's begin by making a drawing. I will draw a vertical line to represent the side wall, and then two sides coming out of the wall, and then one opposite. The two sides adjacent to the wall we will call X, and the side opposite the wall we will call Y. Now, we want to maximize the area, so we know that area is equal to length times width, what we can represent as X times Y. We have a constraint. That constraint is the amount of fencing we have. And so for the two sides of X plus Y, we have 50 feet of fencing. The area to be maximized is in terms of two variables, so we're going to use some algebra to isolate one of the variables. We can say y is equal to 50 minus 2x. And then we will substitute for the area. X times y will express this area in terms of x. So we'll have x times, and where the y was, we'll replace it with 50 minus 2x. Multiply through, and the function we end up with is 50x minus 2x squared. We need to maximize area, which is 50x minus 2x squared. So let's take the derivative. We'll use the second derivative test, and in order to do that, we must begin by finding critical values, if any. Critical values is where the derivative equals 0 or the derivative is not defined. So the first derivative would be the derivative of 50x is just 50 minus the derivative of 2x squared, bringing the 2 down, would be 4x. Setting this equal to 0, we would have 0 is equal to 50 minus 4x. Continuing to solve, 4x equals 50, and we get a critical value of 50 divided by 4, which is 12.5. Now, let's proceed with the second derivative test. So we need to find the second derivative function. The second derivative of, we're working now with the first, so the derivative of 50 is 0, and the derivative of negative 4x is negative 4. This tells us that regardless of which value you put in, the second derivative remains negative. If the second derivative is negative, then we know that it's concave down. And if it's concave down, the most extreme point gives a max. So at x equals 12.5 feet, and we need a y equals, so to solve for y, we have that y is equal to 50 minus 2x. Y equals 50 minus 2 times 12.5, which is 50 minus 25, or 25 feet. So we have x equals 12.5 feet and y equals 25 feet. In part B, what is the maximum area? Now that we have for the side adjacent is 12.5 feet and the side opposite is 25 feet, the area is the product of the length times the width, which would be 12.5 times 25 feet, which is 312.5 feet squared. Example 2. Find the dimensions of a rectangle of area 225 square centimeters that has the least perimeter. What is the perimeter? I began this minimization problem by drawing a rectangle, designating one set of sides as x and another set opposite as y. What we want to do is minimize the perimeter, so the objective function would be p, and the perimeter is the sum of the two opposite sides, so 2x, plus the other opposite sides, 2y. A constraint given in the statement of the problem is that the area, which we know as x times y, is 225. Now we're going to go ahead and solve for y, so we get 225 divided by x, and that's equal to y. We need our objective functions in terms of one variable, so we'll take the perimeter, which we know as 2x plus 2y, and to make it a function of x, p of x equals 2x plus 2, and where the y was, we'll replace it with its equivalent x form, which would be 225 divided by x. We'll do some algebra, and we'll get p of x equals 2x plus 2 times 225 is 450. And to make it easier to differentiate, we'll write the 1 over x as x to the minus 1. So what we need to do then is to use a derivative test to minimize the function p of x equals 2x plus 450x to the minus 1. In order to use a derivative test, we first begin by finding critical values, if any. Critical values are where the derivative equals 0 or the derivative is undefined. Now let's take the derivative. P prime of x is equal to, the derivative of 2 times x is just 2. The derivative of 450 times x to the minus 1. We bring the minus 1 down and multiply it to the 450, so that'll be minus 450. And then x to the minus 2, because we subtract. Now let's set that derivative equal to 0. 0 is equal to 2 minus, and I'm going to write this 450 over x squared. Let's begin to solve for x. I'll add 450 over x squared to both sides. So I get 450 over x squared equals 2. And continuing, let's cross multiply so that we get x squared is equal to 450 divided by 2, which is 225. And when you solve for x, you get negative 15 and positive 15. Now at this point, common sense kicks in and says negative 15 cannot be a measurement because we're looking at a physical quantity. Even so, we still have not demonstrated that the positive 15 gives us the minimum parameter. So we must continue with the second derivative test. That means we're going to take the derivative of the first derivative, and the second derivative would be the derivative of 2 is 0. Now we've got negative 450 times negative 2. That would be positive 900. X to the subtract 1 from negative 2 is negative 3. So we need to evaluate positive 15 and the 900 divided by where the x was. We'll put in 15 cubed. I'm not going to compute this. What I do know is that a positive number divided by a positive number is positive. And if the second derivative is positive, so if the second derivative is positive, then we know that it is concave up. And if it's concave up, the most extreme point is a minimum. We have demonstrated that at x equals 15, I believe the units of measurements were centimeters, we have a minimum. Now we were asked to find the minimum perimeter. So the perimeter is 2 times 15 plus, and 2 times, we've got to solve for y. Y is equal to 225 divided by x, which would be 225 divided by 15, which is 15. 2 times 15 is 30. Plus 2 times 15 is 30, so 30 plus 30 gives us 60 centimeters. So the minimum perimeter for this rectangle is 60 centimeters. Example 3. From a thin piece of cardboard, 8 inches by 11 inches, square corners are cut out so that the sides can be folded up to make a box. What dimensions will yield a box of maximum volume? What is the maximum volume? Let's begin by making a drawing. So here is a depiction of an 8 by 11 inch piece of cardboard, and we'll make the shorter side 8 inches and the longer side 11 inches. The instructions are that we cut out corners, square corners of side length x. And so let's use that to come up with new measurements. For the shorter side, it'll be 8 minus 2x. And for the longer side, it will be 11 minus 2x. Now, before we proceed, let's remember we are making a box. So, with the smaller measurements, we'll do this. The side has to be strictly greater than 0, otherwise you don't get a box. So, solving for 8 minus 2x is greater than 0. We get x is greater than 2x. And furthermore, dividing by 2, we get 4 is greater than x. And of course, x has to be greater than 0. So the possibility is that we could have a box of 0 volume. It doesn't make sense to have a box of negative volume. So we have endpoints of 0 and 4 to remember. Now with that, let's come up with our objective function. Our objective function is that we want to maximize the volume, and the volume of a rectangle is the length times the height times the width. The measurements we have for our box are 8 minus 2x times 11 minus 2x and the height of x. We'll multiply these together and we'll get the volume in terms of x is 4x cubed minus 38x squared plus 88x. So we have our objective function, and now we are ready to maximize v of x equals 4x cubed minus 38x squared plus 88x, remembering that x has to be between 0 and 4. We begin this by looking for critical values. Critical values are where the derivative equals 0 or the derivative is undefined. Let's find the derivative. The first derivative would be bringing down the 3 times 4 is 12, x, subtracting 1 from the power, squared, minus 38 times 2 would be 76x, and then the derivative of 88x would just be 88. Now we need to set this equal to 0, and in order to set this equal to 0, we need to use the quadratic formula. So we're going to use the quadratic formula with a equals 12, b equals negative 76, and c equals 88. So x is equal to the negative of b is negative 76, plus or minus the square root of b squared, negative 76 squared, minus 4 times AC. A is 12, C is 88, and all of this is divided by 2A, so 2 times 12. Using a calculator and rounding to 3 decimal places, we get 2 possible values for x. We get that x is approximately 1.525, and x can also be approximately 4.808. Let's observe that 4.808 is not in our interval, so that one gets thrown out. Even so, we still have not demonstrated that the one remaining value will give us the maximum area or volume. So in order to determine that it does, we're going to use the second derivative test and find the second derivative of the function. So the second derivative of the original function would be, 12x squared. That derivative would be 24x. And then the derivative of negative 76x is minus 76. The derivative of 88 is a constant, so we don't need to, that becomes 0. Let's evaluate the second derivative at 1.525. Compute, and you get the value that is negative. If it is negative, then we know that it is concave down. And if it is concave down, we have the value as a maximum. We're not quite done. So we need the dimensions. That gives us the maximum. The corner cut we determine to be 1.525. Then one of the sides we know is 11 minus 2x, which would be 11 minus 2 times 1.525. And that, using your calculator, gives you approximately 7.95. The other side is 8 minus 2x, which would be 8 minus 2 times 1.525. And that computed is 4.95. So the dimensions are 1.525 inches by 7.95 inches by 4.95 inches. And the maximum volume, if you multiply these together, is 1.525 times 7.95 times 4.95, which is approximately 60.10256. And don't forget the dimensions, inches cubed. This also checks in the function That is, if you do the volume that we had at 1.525 and solve it for 4 times 1.525 cubed minus 38 times 1.525 squared plus 88 times 1.525, you will get 60.0126 inches cubed. Notice we got the same value, and we should have.